Welcome! In this session, we will dive into LeetCode problem number 110, Balanced Binary Tree. This problem focuses on determining whether a binary tree is balanced, which is a fundamental concept in tree-based data structures. We'll explore the problem, examine different approaches, and evaluate their efficiency. Let's get started. In this problem, we are tasked with determining whether a binary tree is a balanced binary tree. A binary tree is considered balanced if, for every node, the depths of its left and right subtrees differ by no more than 1. To solve this, you will write a function that receives the root of a binary tree as input and returns a Boolean value, true if the tree is balanced and false otherwise. The input is represented as a tree node, which includes properties like the node's value, a reference to its left child node, and a reference to its right child node. The output of the function will depend on whether the depth condition is satisfied throughout the entire tree. Now, let's explore some examples to better understand the problem. In the first example, we are given a binary tree with the following structure. The root node has a value of 3, with a left child of 9 and a right child of 20. The node 20 itself has two children, 15 on the left and 7 on the right. This tree is represented in array form as 3, 9, 20, null, null, 15, 7. Based on this structure, the output of the function is true, indicating that the tree is balanced. Let's break down why this is the case. To determine if the tree is balanced, we examine the depth of the subtrees at each node. Starting at the root node, which is 3, the left subtree has a depth of 1, as it only contains the node 9. The right subtree has a depth of 2, as it includes the path to nodes 20, 15, and 7. The difference in depth between the left and right subtrees is 1, which meets the condition of being less than or equal to 1. Looking at node 20, its left and right subtrees each have a depth of 1, so the difference is 0. All other nodes are either leaf nodes or have balanced subtrees. Since all nodes satisfy the depth condition, the tree is height balanced. In the second example, the binary tree is represented as 1, 2, 2, 3, 3, null, null, 4, 4. Visually, it has a root node of 1, with left and right children of 2. The left subtree of the first node 2 contains two levels, with nodes 3 and 4, while the right subtree is empty. For the root node, the left subtree has a depth of 3, while the right subtree has a depth of 1. The difference in depth is 2, which exceeds the allowed limit of 1. Therefore, the tree is not balanced, and the function will return false. In the third example, we consider an empty tree, which is represented as an empty array or null. By definition, an empty tree is always considered balanced, as there are no nodes to create an imbalance. The function will simply return true in this case. To summarize, the problem has constraints ensuring that the tree will have between 0 and 5,000 nodes, and the values of the nodes are within a specific range. It's important to handle edge cases, such as empty trees or highly skewed trees, efficiently to ensure the solution works for all scenarios. To solve the problem of determining whether a binary tree is balanced, one approach we could consider is the brute force method. The idea here is to recall that a balanced binary tree is defined as a tree where, for every node, the depth of its left and right subtrees cannot differ by more than 1. Using this intuition, the brute force approach involves recursively calculating the height of the left and right subtrees for each node, then comparing these heights. If the absolute difference exceeds 1 for any node, the tree is deemed unbalanced. While the process is straightforward, the inefficiency lies in the repeated height calculations. In terms of time complexity, this approach can take n squared, in the worst case, especially for skewed trees, because each node's height calculation involves revisiting all nodes in its subtrees. The space complexity is h, where h represents the height of the tree, as the recursion stack grows with the depth of the tree. While simple to implement, this method is impractical for larger or deeper trees because of its repeated work and inefficiency. To address the inefficiencies of the brute force method, we can turn to an optimized approach that leverages post-order traversal. This approach is built on the intuition that instead of recalculating subtree heights multiple times, we can determine both the height and balance condition during a single traversal. Here's how it works. We use a helper function that returns two pieces of information for each node: its height and whether the subtree rooted at that node is balanced. For each node, we first recursively determine the height and balance status of its left and right subtrees. If either subtree is unbalanced or their height difference exceeds 1, we mark the entire tree as unbalanced. Otherwise, the current node's height is computed as the maximum of the left and right subtree heights plus 1. This method is highly efficient, with a time complexity of O(n), since each node is visited exactly once. The space complexity remains O(h) due to the recursion stack, where h is the tree's height. By avoiding redundant calculations and combining the height computation with the balance check, this approach is both elegant and efficient. The optimized approach is our chosen strategy because it strikes the perfect balance between clarity and efficiency. Its linear time complexity of O(n) ensures that each node is processed only once, addressing the inefficiencies of the brute force solution, which suffers from redundant height calculations. The key insight here is that height and balance information can be computed together in a single traversal, significantly simplifying the implementation. While the brute force approach may seem simpler conceptually, its repeated work makes it impractical for larger or deeper trees. On the other hand, the optimized approach makes better use of recursion, which aligns naturally with the structure of trees, resulting in cleaner and more efficient code. Iterative methods were not considered in this case, as recursion provides a more intuitive way to navigate the tree structure. In summary, the optimized approach is the ideal choice for solving this problem, offering both performance and clarity while avoiding unnecessary complexity. To determine if a binary tree is height balanced, we need to ensure that for every node in the tree, the height difference between its left and right subtrees is at most 1. This leads us to a recursive approach. First, check if the left and right subtrees of a node are balanced, then, compare their heights to confirm that the absolute difference is within the allowed range. To implement this, we define a helper function, check_balance, node, which will perform the heavy lifting. The base case for this function is straightforward. If the current node is none, we return that the tree is balanced and its height is 0, since an empty tree is inherently balanced. Otherwise, we move on to the recursive case, where we will evaluate the left and right subtrees of the current node in order to determine whether the node itself is balanced. To continue, we calculate the height difference between the left and right subtrees using the absolute value of their respective heights. For the current node to be balanced, both subtrees need to be balanced, and the height difference must not exceed 1. Additionally, the height of the current subtree can be computed as 1 plus the maximum height of its left and right subtrees. A naive implementation of this approach could lead to inefficiencies because it might repeatedly compute the height of the same subtree multiple times. This would result in a time complexity of O(n) squared in the worst-case scenario. To optimize this, we ensure that both the balance status and height are returned in a single traversal. By doing so, we can achieve a more efficient solution with a time complexity of O(n). The implementation of this optimized approach is straightforward. Let's write a function is_balanced, root, that utilizes our check_balance helper function to determine if the tree is balanced. In the implementation, the check_balance function will first handle the base case, returning true and a height of 0 for an empty tree. It then recursively checks the left and right subtrees, obtaining both their balance status and heights. Using this information, we determine if the current node is balanced by ensuring that both subtrees are balanced and the height difference is at most 1. The height of the current subtree is calculated as 1 plus the maximum of the left and right subtree heights, and both the balance status and height are returned. The recursion begins at the root node, and the final result of whether the tree is balanced is returned by the is_balanced function. Some key insights into this approach include how the problem is broken down recursively, how we achieve efficiency by combining balance checks and height computations, and how we can terminate early if an unbalanced subtree is encountered. These components ensure that the algorithm runs efficiently with a time complexity of O(n). The algorithm uses the call stack for recursion, which implicitly stores intermediate results for each node. In terms of complexity, the time complexity is O(n), because every node in the tree is visited exactly once. The space complexity is O(h), where h is the height of the tree, because the recursion stack's depth depends on the height. For edge cases, an empty tree is always balanced, as there are no nodes to compare. A tree with a single node is also balanced, since it has no subtrees. On the other hand, a highly imbalanced tree, such as one where all nodes only have left or right children, will still be evaluated efficiently, thanks to the early termination mechanism. To illustrate this, consider a tree where the root has 2 children, and one of those children has its own 2 children. This structure allows us to see how the algorithm handles a moderately balanced tree. Starting with the root node, we first examine its left subtree. For the left child, we check its left and right subtrees, both of which are leaf nodes with no children. Since their heights are both 0, the subtree rooted at this node is balanced, with a height of 1. We then compute the height of the left subtree, which is 2. Similarly, the right subtree of the root is a single node with no children, so it is balanced with a height of 1. At the root, the height difference between the left and right subtrees is 1, which means the entire tree is balanced. The height of the complete tree is 3. This step-by-step process confirms that the tree is balanced, and the algorithm returns true as the final output. Here, we define a class called solution with a method isBalanced that determines if a binary tree is balanced. Inside this method, we define a helper function called check_balance, which will recursively compute the height of each subtree and check if it is balanced. If the current node is null, we return a height of 0 and mark it as balanced since an empty tree is inherently balanced. Next, we recursively call check_balance on the left subtree of the current node. If the left subtree is unbalanced, we exit early by returning 0 for the height and false for the balanced status. Similarly, we check the right subtree in the same way. Once both subtrees have been evaluated, we determine if the current node is balanced by checking if the difference in height between the left and right subtrees is at most 1. Finally, we compute the height of the current node as the maximum height between the left and right subtrees, plus 1 to account for the current node itself. This function then returns the height and whether the subtree rooted at the current node is balanced. After defining the helper function, we kick off the recursive process by calling check_balance on the root of the tree. The result is a tuple, but we only need the second value, is_balanced, which indicates whether the entire tree is balanced. This value is then returned as the output of the isBalanced method, completing the implementation. By using this approach, we ensure that the tree is evaluated in a single traversal, making the solution efficient with a time complexity of O(n), where n is the number of nodes in the tree. Here, we begin the Java implementation by defining the structure of our binary tree node using a static nested class called treeNode. Each tree node stores a value, as well as references to its left and right child nodes. The constructor initializes these fields, defaulting the child nodes to null. Moving forward, the isBalanced method is defined, which serves as the entry point for our solution. This method takes the root of the tree as its argument and relies on a helper function, checkBalance, to determine if the tree is balanced. The checkBalance function is designed to recursively traverse the tree, starting with the root. If the current node is null, meaning we've reached a leaf, it returns a new balanced status object with a height of 0 and a balanced status of true. Next, the function proceeds to evaluate the left subtree by calling checkBalance on the left child of the current node. If the left subtree is determined to be unbalanced, the function immediately returns a balanced status object indicating an unbalanced state. Similarly, the function checks the right subtree. If the right subtree is unbalanced, the result is also returned as unbalanced. Once the left and right subtrees are both processed, their respective heights and balance statuses are used to evaluate the balance condition for the current node. A node is considered balanced if the absolute difference between the heights of its left and right subtrees is less than or equal to 1. The height of the current node is then calculated as 1 plus the maximum height of its left and right subtrees. Finally, a new balance status object is created, storing the calculated height and the balance status for the current node. This object is returned to the caller, which allows the function to propagate balance information up the recursion stack. To demonstrate the implementation, we create a sample binary tree in the main method. A root node is instantiated with the value 1, and its left and right children are assigned the values 2 and 3, respectively. Further, the left child of node 2 is set to 4, and its right child is set to 5, forming a small, balanced tree. We then create an instance of the solution class and call the isBalanced method, passing the root of the tree as an argument. The result, which indicates whether the tree is balanced, is printed to the console. In this case, the output is true, as the tree satisfies the balanced binary tree condition, where the height difference between the left and right subtrees at every node does not exceed 1. Here, we are analyzing a balanced binary tree. We start at the root node, which is node 1, and call the check_balance function. From there, we traverse to the left child, node 2, and again call check_balance. Going further down, we move to the left child of node 2, which is node 4. Since node 4 is a leaf node with no children, the left and right subtree heights are both 0, and it is balanced. Using this, we calculate the height of node 4 is max 0, 0, plus 1 equals 1 and confirm that it remains balanced. We then return a height of 1 and a balanced status of true for node 4. Next, we move to the right child of node 2, which is node 5. Similar to node 4, it is also a leaf node. So, we return a height of 1 and a balanced status of true for node 5. With both child nodes processed, we now focus back on node 2. At node 2, we calculate the height and balance status based on its children. The height is determined as max 1, 1, plus 1 equals 2, and the tree remains balanced because the height difference between the left and right subtrees is abs 1 to 1 equals 0, which is within the allowed limit of 1. We return a height of 2 and a balanced status of true for node 2. Now, we traverse to the right child of the root, which is node 3. Node 3 is a leaf node with no children, so its height is 1 and it is balanced. Finally, we calculate the height and balance status of the root node, node 1. The height is computed as max 2, 1, plus 1 equals 3, and the tree remains balanced because the height difference between the left and right subtrees is abs 2 to 1 equals 1. Therefore, we conclude that this binary tree is balanced, and the function returns true. Now, let's look at an example of an unbalanced binary tree. Starting at the root, node 1, we call check_balance and move to its left child, node 2. From node 2, we traverse further down to its left child, node 3. Since node 3 is a leaf node with no children, we calculate its height as max 0, 0, plus 1 equals 1 and confirm that it is balanced. Returning to node 2, we calculate its height and balance status. The left subtree height is 1, and the right subtree height is 0. This gives a height of max 1, 0, plus 1 equals 2, and the tree remains balanced because the height difference is abs 1 to 0 equals 1. We return a height of 2 and a balanced status of true for node 2. Returning to the root node, node 1, we calculate its height and balance status. The left subtree has a height of 2, while the right subtree has a height of 0. This gives a height of max 2, 0, plus 1 equals 3, but the tree is now unbalanced because the height difference is abs 2 to 0 equals 2, which exceeds the allowed limit of 1. Therefore, this binary tree is unbalanced, and the function returns false. Finally, let's consider a simple example with a single node tree. The binary tree consists of just the root node, node 1. Since node 1 has no children, the left and right subtree heights are both 0. We calculate the height of node 1 is max 0, 0, plus 1 equals 1, and since there is no height difference, the tree is balanced. The function concludes that this binary tree is balanced and returns true. The time complexity of this solution is O, n, where n represents the number of nodes in the binary tree. This is because the helper function, check_balance, is called recursively for every node in the tree. Each node is visited exactly once, and during the visit, we perform a constant amount of work, such as calculating the height and checking if the node is balanced. Since the function operates on each node individually, the total number of recursive calls is proportional to the number of nodes, leading to O, n, time complexity. To understand this mathematically, let T, n, be the time complexity for a tree with n nodes. At each node, constant work is performed, and recursive calls are made to the left and right subtrees. This can be expressed as T, n, equals T, left underscore subtree, plus T, right underscore subtree, plus O, 1. Since all nodes are visited exactly once, the overall time complexity simplifies to O, n. Now let's look at the best, average, and worst cases for time complexity. In the best case, when the tree is empty and n equals 0, no recursive calls are made, so the time complexity is O, 1. In the average case, for a balanced binary tree, all nodes are visited during the traversal, resulting in O, n. Similarly, in the worst-case scenario, such as a completely unbalanced tree where nodes are arranged like a linked list, all nodes are still visited, so the time complexity remains O, n. Moving on to space complexity, it is determined by the depth of the recursive call stack, which depends on the height of the tree, denoted as h. In the worst case, the maximum recursion depth is equal to the height of the tree, leading to O, h, space complexity. For a balanced binary tree, the height is approximately log n, resulting in O log n space complexity. However, for a completely unbalanced tree, the height equals n, so the space complexity becomes O n. Additionally, the solution does not use any extra data structures, so the additional memory usage is negligible. Considering the best, average, and worst cases for space complexity, in the best case, if the tree is empty, there is no recursion, and the space complexity is O1. For the average case, in a balanced binary tree, the height is approximately log n, resulting in O log n space complexity. In the worst case, for a completely unbalanced tree, the height is equal to n, leading to O n space complexity. This demonstrates that the space complexity is directly tied to the height of the binary tree, which varies depending on its structure. Now let's compare this optimized approach to a brute force approach. In a naive solution, you would calculate the height of each subtree repeatedly, leading to significant redundant computations. For each node, the heights of the left and right subtrees would be recalculated multiple times. This results in O n squared time complexity in the worst case, as every node triggers a traversal of its subtrees. In contrast, the optimized solution avoids this redundancy by calculating the height and balance together in a single traversal, reducing the time complexity to O n. To provide a mathematical perspective, the brute force approach has a nested traversal pattern, where the time complexity is O n multiplied by O height, resulting in O n squared, for unbalanced trees where the height equals n. The optimized solution eliminates this inefficiency by visiting each node only once and propagating height information up the recursion stack, ensuring O n time complexity. For space complexity, both approaches rely on recursion, so their space usage is dominated by the call stack depth, which is O h. However, the optimized solution is significantly faster in practice due to its elimination of redundant calculations. When working with balanced binary trees, there are some common mistakes that are important to avoid. First, it's critical to understand the difference between a balanced binary tree and a complete binary tree. A balanced binary tree only requires that the height difference between the left and right subtrees of any node is at most 1, whereas a complete binary tree has stricter requirements every level, except possibly the last, must be fully filled. Confusing these definitions can lead to incorrect logic in your implementation. Another frequent mistake is neglecting to handle null nodes properly. Forgetting to account for null nodes when calculating heights or making recursive calls can result in runtime errors. Additionally, when using a recursive approach, recalculating the height of the same subtree multiple times can create inefficiencies, leading to exponential time complexity. This issue can be avoided by adopting a bottom-up approach. It's also crucial to consider edge cases like a tree with only one node or a tree with a single subtree, as these are often overlooked. Finally, be cautious with global variables in recursive solutions. If they are not handled correctly, especially in environments where multiple test cases are run, they can cause incorrect results or unexpected behavior. In interviews, understanding patterns and trade-offs is essential for solving tree-related problems effectively. Many of these problems can be approached using recursion combined with divide-and-conquer techniques. Recognizing when to apply these strategies can save you significant time. While a brute force solution may be easier to implement initially, it's inefficient for large trees since it has a time complexity of O n squared. Interviewers often expect you to optimize this to O n by using a bottom-up approach. Beyond implementing the solution, you should also clearly articulate how your logic accounts for all edge cases and why your optimization is necessary. It's common for interviewers to pose follow-up questions, such as asking you to validate balance under stricter definitions like those used in AVL trees, or even to modify the tree to make it balanced. To strengthen your preparation, it's helpful to explore related problems like LeetCode 104 for maximum depth, LeetCode 111 for minimum depth, and LeetCode 543 for the diameter of a binary tree. These problems share overlapping concepts and can deepen your understanding of tree structures and recursion. Now let's look at some alternative approaches for solving the problem of determining whether a binary tree is balanced. The recursive top-down approach involves calculating the height of the left and right subtrees for each node and then verifying the balance condition. This method is straightforward to implement, but it's inefficient, with a time complexity of O n squared, because the height of subtrees is repeatedly recalculated. A more efficient alternative is the recursive bottom-up approach. Here, you traverse the tree in postorder and compute both the height and the balance status of each node simultaneously. This method achieves O(n) time complexity, making it more suitable for interviews, though it does require a deeper understanding of recursion. Lastly, there's an iterative approach using breadth-first search. This involves performing a level-order traversal while keeping track of the height of each node using additional data structures. While this approach avoids recursion stack overflow and may be useful in environments with limited recursion depth, it can require more memory to manage the extra data structures. Each of these methods has its trade-offs, so it's important to choose the one that best fits the constraints of the problem you're solving. Great job! To summarize, we analyzed the balanced binary tree problem, explored its solutions, and highlighted key takeaways. Keep practicing tree-based problems to strengthen your skills. If you enjoyed this, subscribe for more solutions, and I'll see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!